Good morning, students. Welcome to the mass transfer course. Today will be lecture 19. Here we are discussing about the interface mass transfer. And in interface mass transfer, we are discussing about the material balance, and from the material balance we will get the operating line. There are four cases: the steady state counter current, steady state co-current, steady state cross current, and fourth one is steady state mass transfer in phase wise contact of two phases. In last two lectures we understand how to construct the operating line for the first three cases. These are steady state counter current process, steady state co-current process, and steady state cross current process. Today we will look after the steady state mass transfer in stage wise contact of two phases. Actually, the concept is like this. In first two cases, steady state counter and steady state co-current or oscillation, generally we use backplate or a continuous process. But we understand now in a single. So if it is a continuous process, so one equilibrium can be attained. And we have seen that if we come up to the equilibrium, then maximum mass transfer I will get. But once we will reach to the equilibrium, thereafter no mass transfer is possible. The concept is that can we make multiple equilibrium stages in a single equipment? Because once I will reach to the equilibrium for a case, so up to the equilibrium we will get the mass transfer. That is maximum mass transfer is possible. So, but if you take the counter current or co-current, you can see that only single equilibrium you can reach. One time you can reach the equilibrium. Cross current, okay. So there are three units, but these are physically separated units. So that, but if you see in cross current, if you make three physically separate units, then you are getting better mass transfer because you are attaining the equilibrium three times. But is it possible in a single equipment I will make multiple equilibrium stages, or I can create multiple equilibriums? And if we can make multiple equilibriums, then I will get the better mass transfer. The fourth one, the concept is that if you see stage wise mass transfer, steady state mass transfer in a stage wise context. Stage wise contact of two phases mean if you that means in different stages I am creating different equilibrium within a single equipment, and this is the concept here. Okay, so this is the higher version. How can I make this? So this is one typical unit, okay, where I have created multiple stages. So if I can create multiple stages, then I can reach multiple equilibrium. And what is the nomenclature here? Here top is 1. and down is n. If there is number of n number of stages, so there is n. This is the reverse nomenclature of what we have taken for co-current or counter current. In co-current I put down 1 and top 2 because there was only 2 in between, that was the continuous process. But here I am making stage. How will you make the stages? Let's say this is a hollow cylinder. Now if I make a partition here, okay, so this is the partition, so this is the circular one, okay, this is the circular. So I will make one circular partition one, and one part I will cut, and here I will pick whatever, I will make some wire so that when liquid will come from the top, it will hold here, and when the liquid level will be higher than this, then it will come down to the second, and the G phase will come here. So if you take the first stage 1, the first unit, okay, first stage. So what I did, the hollow cylinder is there, here I make a circular plate, okay, and I cut one side, okay, here one side if I cut it, let's take 10%, I cut this one, then if I put this one, and then where I cut this, I will keep 2-inch, that some partition that is called wire, so that here liquid will hold up. So when liquid will come from the top, liquid will hold up, and when the level will be higher than this, then it will come down. And in this plate I made some holes, therefore the gas will come up from this hole. So gas is coming G phase, white, that is coming through this hole upward direction, and I kept the gas flow rate in such a way that there will be no liquid will come down from this hole. Or I made some arrangement that I will discuss later in such a way so that this holes can be done in modified way, so that only gas can come from the bottom to top, but no liquid come down. So liquid will come only when there is overflow. So if I make this, that means, and it is a mixer. So here I am making one stage, and if I allow some time to mix them, then it will reach to the equilibrium. So I will make one stage 1. Now what is the concept here? If it is a stage 1, okay, so from the top, so it is 0 phase upper, so that is coming LS, liquid phase, and that is X0. X0 is coming here, so gas is coming. What gas is coming? Gas is coming from the plate 2. So what is plate 2? From plate 2 is coming, that is Y2, and what is coming out from Y1, that is Y1. Okay, whatever is coming from the plate 1, that is Y1, it is 1, and GS will be constant. This is the gas flow rate, and liquid flow rate 1, 2, 3, so here 0, so X0 LS it is coming, and whatever liquid is coming from the here, that is a concentration X1. So in plate 1, whatever the flow rates are coming to the plate, these are X0 and Y2, these are the coming, this Y2 is coming from the down plate 2, so Y2 GS and LS X0, and what are the concentration leaving from the plates? This is leaving X0 and Y1, X1 and Y1. So X1 and Y1, when they are leaving, if I allow them to reach into the equilibrium, that means they will reach, they will be in equilibrium. So X1 and Y1 will be in equilibrium if I allow it sufficient residence time in this tray, and this is called tray. Okay. Now this is for the first tray. So I make the first tray like this. Let's take I made another tray that is n. Okay, so it is coming down, so it will. Now if I take this one, the nth tray, so what will be nth tray? That down will be n plus 1, so whatever is coming from the down, that is yn plus 1, and whatever will be go up, that is yn, and this will be n minus 1. This is nth plate, this is n minus 1 plate, so from this plate the liquid flow rate is coming the corresponding xn minus 1, and when this from this nth plate whatever liquid flow rate is coming, okay, that is x. Now if you take the capital N, okay, so in this last plate, okay, so top to bottom, 1 2 3 4 small n to capital. It may be sometimes, you know, that plates are in industry typical hundreds, sometimes 10 30. These are the very common real example in industry. If you see that, you know, some distillation column, you have already visited some industry, if you see the distillation column, they are the in this test. Okay, now nth tray, so from here I am putting the gas gs, and what will be the, because this is nth, so n plus 1 will be down, that is yn plus 1, this is coming, and from nth whatever liquid is coming ls, that is a x. So this, so x0 is entering, xn is coming out, and here yn plus 1 is entering and y1 is going out. So nomenclature is little bit different here. If you should keep it in mind when you are discussing about the stage wise contact, then your nomenclature first plate will be 1 and it will go down to up to capital N. But in co-current and counter current, you have to give only 2. Bottom is 1, top is 2. But here 1 2, I can make multiple trays in a single column, single equivalent. And if I make multiple trays, that means I can create multiple equilibrium stages. And if I can make multiple equilibrium stages, I have a better separation. In a single, in cross current also we are creating multiple equilibrium stages. Stage 1, one equilibrium, stage 2, but they are physically separate unit. One mixer, one settler, one unit, then another mixer, another settler, another unit. Okay, but here in a same column, okay, in a same, within a same equipment, I am creating multiple equilibrium stages with creating multiple trays, and generally the difference between the two trays are 1 feet to 3 feet depending on the floors. That I will come later, okay, in detail. So you can understand, if you have a, let's take 10-meter height column, okay, and now if you keep the tray spacing 1 feet, generally 1 feet to 3 feet is that the difference between two trays are 1 feet to 3 feet, means around 0.3 meter to 1 meter. So if you have a 10-meter long column, and if you place the trays 1 feet apart, means in a 3 meter, in a meter you are putting 3 plates. So in 10 feet, in 10-meter height column, you are putting 30 plates. So you are creating 30 equilibrium stages, and we will get that's the concept. Okay. Now if you take the stage, what is stage? The definition: any device or combination of devices in which two immiscible phases are brought into intimate contact in order to achieve mass transfer from one phase to another phase is called stage. isn't it? So if I make a tray, that is one tray. It may be one device or combination of devices. Okay. I will come later in details in chapter 5 the how to create how to construct the trays, how to other things we'll discuss that mechanical design of this equipments we'll discuss in detail. But now just you understand just little bit conceptual thing how we are making the trace. Now this is second point is important. An efficient contact of phases reach equilibrium when they leave the stage is called ideal stage. So what is ideal stage means what I told, if they reach to the equilibrium then it will be ideal state. But fact is that if you want to reach it equilibrium you have to allow the residence time of gas or liquid should be high, but sometimes in practical it is not possible. Sometimes it will come 60% of near to the equilibrium, so then then that efficiency is 60%, but when it will reach to the equilibrium then it is called ideal stage. This leads to stage efficiency. The stage efficiency gives a measure of how close to the equilibrium the phases may reach in a stage. An ideal stage has 100% efficiency. 100% when it will reach to the equilibrium. A group of interconnected stages in which the phases flow from one stage to another in a sequence is called cascade. So this is the cascade. Okay, and in general practically generally stray efficiency generally 60%, but when it will be ideal stage then it will be the stray efficiency will be 100%. That thing also will come. There are different types of efficiencies and that will also will come, we'll discuss later. Now this is the thing. So you have a number, first number of column, first number of tray, then nth tray, okay, 1 2 3 to n and 2 capital. Okay. So now if you take this, let's take stage, if you take that 2 stage tray 2 or stage 2, then what is coming from the top, if this is a 2, if I put it, so from top it is coming x1 and from bottom stage 3 that will, so from 3 what is coming out, that is will be y3. So in stage 2 x1 and y3 are entering and what is going out from x2 and y2, and if stages, this stage is ideal then y2 and x2 will be in equilibrium. But keep it in mind, x1 and y3 will not be in equilibrium because x1 is coming from the top plate and y3 is coming from the bottom plate. So whatever the entry concentration in a particular plate, they will not be in equilibrium, but what are the concentrations are going out from this plate, from plate 2, these are the y2 and x2, they will be in equilibrium if the stage is ideal. Okay, now if you take the nth tray, okay, so if I take the nth tray then upper tray will be n minus 1, okay, and bottom tray will be small n plus 1. So what are the coming for gas phase, from this plate is coming then yn plus 1, okay, and xn stream entering, that will be from the top tray n minus 1, that will xn minus 1. So xn minus 1 and yn plus 1 they are entering, okay, into this nth stage, and what are the coming out from the nth stage, that is yn and xn, and yn and xn will be in equilibrium if this stage is in. So you understand this, how to in each tray what will be the nomenclature. So similarly if you take this one n a capital N, so GS. So what is coming? N plus 1. You consider this. Okay, what is entering? N plus 1 is entering. This is N minus 1. Capital X N minus 1 is entering. What is going out from nth tray? Capital N. That is Yn and Xn it is coming out. Okay. So this nomenclature you have to make little bit practice. Now if you take this envelope 1 up to nth tray. Okay. So if I make this material balance, okay, for up to this, so what is mean? GS it will not change. Okay, GS will be constant. Whatever GS is entering, it will coming out. And what is entering up to this envelope? Yn plus 1 entering, and here outgoing is Y1. So this is the for the G phase. And L phase is what? What is going out? Xn is going out and entering X0. This one. So Yn plus 1 minus Y1, Xn minus X0, that is L. So this is the slope. Ls by Gs. This is same slope as your counter current, isn't it? Now if you take the overall, means whole cell overall balance, then what will happen? Small n, then that will be capital N. Only thing will change that small n will change to capital N. Yn plus 1 and X capital N, and Y1 this same will be this will be your material balance, isn't it? Now if I plot this thing in a plot, okay. So before that, let's take for this one also, that let's take the example of absorption of ammonia from air stream by water. So 10% ammonia is there. Okay, it is, I am putting it from the top, the corresponding inert flow rate, and it is going out, and from top water I am putting it is. So the mass transfer is happening from G phase to L phase. G phase to L phase. Here. So here Yn plus 1 will be higher, Y1 will be lower, and X0 will be lower, Xn will be higher. But here I am creating multiple equilibrium stages. That's the thing. I just made very simple. I made this one circular, circular disc, and fix it to, then I cut it one part so that I can make one stage and with some parts. Now if you take this one, so what is your this is higher and this is higher, isn't it? So as mass transfer is happening from G phase to L phase, so what is this point, end point, that is Xn Yn plus 1. So Xn and Yn plus 1, this is the point here. Okay, end point. And what is this? This is X0, this is low, and Y1, that both are low. So if you take X0 and Y, this is low, and that slope is this. So slope is Ls by Gs, operating line. So this is your operating line, and this is your equilibrium line, isn't it? But the curve is very much similar to your operating line, is very similar to your counter current process, because here also if you see, the counter current is going on. G phase moving from bottom to top, and L phase is coming from top to bottom. So here also the counter current is going, but I created multiple stages. That's all. So now here this is the point I got. Okay. Now if you take the nth tray. Okay, so capital nth tray. So what is going out? So this is the bottom part, and what is top part? That is what is coming, xn minus 1 y. Okay, so my both will be less than xn. xn minus 1 will be lower than the xn, because mass transfer is happening from G phase to L phase. So this is some, let's say this is the value xn minus 1. Okay, and what is yn? Yn will be lower than that is, so this is the value. Okay, now how will we get this? And whatever the xn and yn, these are in equilibrium. Let's take the stage is ideal. So if I come from this point is known to me, if I come down here, so this is the equilibrium point, xn and y. Okay, this is the, because xn and yn, if stage xn and yn are in equilibrium, so it will be on the equilibrium line. Now if you go here in this direction, then once you, because you know this curve, so then you will get this the concentration. And this is this, for this one, the nth tray. For nth tray, in the nth tray, you are bringing down this concentration to this concentration through this equilibrium. Okay, so why this is in on the operating on the equilibrium line? If stage efficiency 100%, must, if stage is ideal, that's mean we allow sufficient time to bring the outgoing stream from this tray, they are in equilibrium, so that xn and yn will be in equilibrium. That's why it is in this on the equilibrium. So this point will be known to you. So now if you take this one and come to this curve, because, and if you take this one, so this is correspond to this triangle, correspond to nth tray. Now from then, if you what we are doing nth tray, then we are getting n minus 1 tray. Okay, so now if you take another, if you come next tray, the upper tray, that you come here, so then that n minus 1 tray, what will be this one? Xn minus 1, yn minus 1, this is n minus 1, sorry. And if you go, then if you reach this one, because it n minus 1 state, then n minus what say, so yn minus 1 will go out from n minus 1 tray, and xn will go out from this thing, and it will enter this thing from the bottom. And then if you go here, if you make another triangle, this is n minus 2 tray, n minus 1 tray. Now if you take another one, this is n minus 3. So in this case, if you see, you need one tray, 2 and 2.5 tray is required to bring your concentration to yn plus 1 to this y, isn't it? So here, how many stages are required, you can calculate easily. So how I am calculating this one? If this point will be known to me, okay, so I'll come down and reach here. This is 1 tray, this is 2 tray, this is 3rd tray. But you cannot make half tray. So you have to, you understand, physically it is not possible. But if you have, okay, let's say this is practically this is 2.5 if I have to bring, but physically you cannot make 1/2 tray, so you have to take the next one. So in this case, to bring this concentration yn plus 1 to y1, I can get this equilibrium. I can get the 3 number of stages, isn't it? So see here, I can calculate the height of the column easily. because I know if the stress spacing, let's take this stress spacing is generally 1 feet to 3 feet, and I will discuss you later when in next chapter in detail that what will be exact spacing. It is told that 1 feet to 3 feet, but generally when flow rates will be high, then it is 3 feet, and when flow rate will be low, it will be 1 feet. Depends on the flow rates, and other conditions are there that I will discuss in next chapter. But once you know the difference between two trays, let's take 1 meter. Now if you get 3 trays, so what will be the height of the column? Your height of the column will be 3 meter. And for a particular case, if you see the tray spacing is 1 meter, and this is 30 number of plates, equilibrium laser. So 30, the height of the column will be 30 meter. And if some cases, if you see the number of triangles are or number of stages are 100, then it will be 100 meter. Because I want to construct this equipment, mass transfer equipment. I know this is circular. Now what other things I need to do? I have to know that what will be diameter and what will be height. Okay. And now from this calculation we are getting the what will be the height and what will be diameter, that also can be calculated. That also I will discuss in next chapter. In next chapter I will discuss how to calculate the diameter of the column. It depends on the flow rate again. I will discuss this one. So once you will get the diameter of the column and height of the column, that's mean you have designed the vessel. You know that what will be the height. Then you trace spacing. So that's mean you have done your job. Because I want to construct one mass transfer equipment for multiple stages. So if I know that height and diameter, it is my job. Okay. So here, this is the one way we have made this thing in graphically. So thing is that we have for this thing we have the equilibrium curve. Then from the material balance we get the operating curve, and I will make the triangle. Each triangle correspond to one stages or tray. So for my system, because this and this point will be known to, these 2 points will be known to mu according to problem. So I can calculate how many stages are required, and according to this trace spacing I can tell easily what will be the height of that. Also, the number of stages can be calculated. This is one method. This is graphical method, and there is some analytical method also. And what is this analytical method? That is called Kremser equation. In Kremser equation, taking this same thing, I can calculate. I am not going to in detail in this calculation. It is given in the book. But thing is then here one thing, important thing, that theoretical number of plates for absorption n, okay, log y n plus 1 minus alpha is what? Alpha is absorption factor, equilibrium, okay, Henry constant, alpha x0 y1 minus alpha x0, that is, this is the equilibrium constant, into 1 minus 1 by a plus 1 by a by log a. For absorption, this is the theoretical number of stage. Theoretical number of stage means it is assumed the efficiency is 100%. Stages are ideal. And now here we know everything. These are the concentration term, and this is the equilibrium constant. For gas liquid it is Henry constant, okay, alpha. And what is A? A is LS by GS. LS by GS means what? Slope of the operating line by alpha. Alpha means slope of the equilibrium line. So absorption factor, and this is called absorption factor A. This is the slope of the operating line by slope of the equilibrium line. If slope of the operating line and slope is equal, means when it is equal means these two lines will be parallel, then absorption factor will be 1. And if absorption factor is 1, okay, then this log A, this will be 0. So then this thing will not be applicable. You cannot calculate this through this Kremser equation. Then you have to do it through graphical method. But other than this, when absorption will not be equal to 1, then you can calculate the theoretical number of plates. For absorption, this is the equation, and for stripping, this is the equation where x0 minus yn plus 1 by alpha by xn yn plus 1 minus alpha 1 minus a plus 1 minus a bar log 1 minus a bar. Okay, and this is 1 by a equal to stripping factor. Okay, a is absorption factor LS GS by alpha, stripping factor is different, alpha by LS GS. So 1 by a is the stripping factor. Okay, sometimes it is called S bar. Sometimes you will see, because if you take this equation absorption factor, if you take the instead of tipping, so this will be S bar. Okay, so same, and it will be 1 by S bar, and it will be 1 by A. So 1 by S. So equation will look like similar, but you can use either of these two equation, and this is very well known equation. This is Kremser equation. But with this Kremser equation, you can calculate theoretical number of plates. For absorption, there is one equation, and for stripping, this is the equation. But when absorption factor not equal to 1. But keep it in mind, Kremser equation is applicable for calculating theoretical number of stages in multiple contact. Okay, so slowly we are moving how to design our mass transfer equipment. Here we can understand now, for a particular multiple stage equipment, what will be the height of that. We are getting some conceptual thing. Later we will discuss it more elaborately. Thank you for your attention, and have a nice time.